Okay, so today, before we go over limiting reactants and combustion analysis problems, I want to work that number 4 from last night's homework because I think it's worth talking about. So that was homework H, right? G, homework G. Yeah, I'm on top of things. So I need to change my pen size here. I don't know how to set the default on this. Every day I have to do this. Okay, so looking at number 4, everyone have that out? Because I think a lot of you looked at the key and said, oh, okay, that looks good. I wrote it down. An element X forms both a dichloride and a tetrachloride. So X forms these two things. What are the only possible metals that could just form those? Transition, I want more specific. So what is this saying the metal's charges are? A +2 and a +4. So what are my only options that you know for sure only form those two charges? Yep, and those are my two options for my unknown. So we either have a tin or a lead attached to the chlorine. So your job is to figure out which one it is. So this problem starts by giving you some information, and writing a reaction is the way to go because it says treatment of 10 grams of XCl2 with excess Cl2 forms 12.55 grams of XCl4. That's all they give you, and they want you to find the atomic mass of X, meaning is it tin or is it lead? So looking at this, we have these 2 gram things. What can I figure out based on the knowledge of the 2 grams? Conservation of matter. How many grams, yes, Nick, how many grams of Cl2 you have, which would be what? 2.55. So Cl2 in this reaction apparently weighs 2.55. Do you think this Cl2 weighs different than that Cl2? No. So we know the Cl2 in this also weighs 2.55 grams. The whole thing weighs 10.00 grams. What did I just calculate there? Your percent of Cl in that compound. And that came out to be, what was it, 20, y'all have it in front of you, 25.5%, right? So that's all we need really, because what this is telling us is whatever compound we choose, be it PbCl2 or SnCl2, whichever one of these is 25.5% chlorine, that's the one we choose. So how do I find the percentage of chlorine in these? Do it percent by mass with the molar masses, right? So I take the mass of Cl over total times 100, and then I take the mass of Cl over total of this one times 100. When you do that, the PB turns out to be the answer, and this one came out to be like, was it the PB? It was the PB, right? And this one came out to be like 37 or something like that percent. So it's not too bad of a problem, right? It's just knowing where to go with it. Okay, so y'all ready for limiting reactants? Okay, I need people with calculators. Since you're people on film today, I need you ready to do some calcs. Did you just say what up? That was you? All I heard it was from that general direction. Someone said what up. Yeah, the thing is, it's really, you'll be surprised how much of y'all you don't hear on here. It's just me talking. Okay, so in this problem, we're supposed to determine the moles of both the CO2 and the H2O formed when 2 moles of ethane is reacted with 10 moles of oxygen. Oh, it's not 366. 10 moles of oxygen. So ultimately, we're going to have to do stoichiometry twice, once to here and once to here. But if you notice, we have grams of both. Which one do I do stoichiometry from? Just guess. Pick straws. Rock, paper, scissors. How do I know which one to do? I heard someone say oxygen. Is that an educated guess, or are you just like 50-50ing it? Y'all have done this before. I'm not asking what to do specifically. What do you need to find? What's the title of this slide? Oh my God. What do I need to do? Find the limiting reactant. Oh my goodness. Sorry, people at home. So one of these two things is limiting and one is an excess. Does everyone get that? Okay, I wasn't asking for specifics. I just want to, in general, we need to find the limiting reactant. In the problems we've done with stoichiometry up to today, we only had one of the reactants, and the other one I'd put an X through because it was an excess. Well, that's not the case here. So we need to find the limiting reactant. The first step in my class is always to find moles of your reactants. Well, this problem's nice. It gave it to us in moles. The majority of problems you get are not going to be in moles, so they'll usually give you grams, and I want you to convert those to moles. So here we have 2 moles of the C2H6, and we have 10 moles of the O2. So that's the first step. Then the second step is based on the coefficients. So if you notice, there's a 2 to 7 relationship there, okay? Based on the fact for every 2 of these, I need 7 of these, I'm going to have to take that into account when I'm looking at my number of original moles. I can't just say, oh, there's less moles of this, so I want to use that. Not necessarily. It depends on this mole ratio. It's kind of like if I bought a loaf of bread from the grocery store, and then I bought one of those huge Costco thing of pickles. I'm trying to make sandwiches. Which one is going to run out first? The bread will. And how do you know how many sandwiches you'll make from the bread? What do you divide by to figure out how many sandwiches you make from the bread? 2, because you need 2 pieces, versus maybe you need 5 pickles. So if every sandwich has 5 pickles, you divide that big thing by 5, and you divide the loaves of bread by 2 to figure out how many sandwiches you make. Whichever number comes out less is the number that's limiting. So that's what we're doing here. We're going to divide this 2 moles of this guy by the coefficient in the balanced equation. So we get 1 there. This number is not moles anymore. We're just using it as a comparing number. And what is the 10 divided by? 7. And what do you get for that? It's greater than 1. I'm okay with that. What was it, 1.4 something? Okay, cool. Do the calculations quickly. Oh my God. So this one is smaller than this. Therefore, this is the limiting reagent, and this one is in excess. So we're going to do stoichiometry from our ethane to our 2 products. Okay? So now we just do normal stoichiometry, starting with our moles. Again, don't use these numbers again. That's just a comparing number. So we have 2.00 moles of C2H6. Now I'm going to mole bridge over, what do you want to go to first, CO2 or H2O? Doesn't matter. CO2. So for every 4 moles of CO2, I have 2 moles. Woo, good thing. Good thing I don't need a calculator on this. How many is it? So we need 4 moles. The question's asking for moles. Determine moles of this. This is a really nice problem. You're usually going to have to go from grams to grams all the way. So seeing that the 2 and the 2 cancel no matter what, how many moles of water do we need? 6. Do we have to figure that out, or do y'all get it? Let me, I can't see the scroll bar. This is going to be another great video. Another great video. Okay. So yeah, it's 6 because all I'm changing is this number, right? For every 2 moles, I have 6. So it's 6 moles of H2O. We good? So let's do the next problem, which is a little more indicative of the level of problem that is going to be very, very common. It says calculate the mass of calcium nitride formed. So we're looking for the grams of this when we have 50 grams of each of these reactants. Okay? So, which one do we use? Do we know? No. What do we have to determine? Which is the limiting reagent. So, I'm going to do calcium first. Calcium, I have 50 grams. I'm going to divide by the molar mass of calcium to get moles, which is 40.08. Somebody get that calculated. Thank you, 1.24 moles. And then R and 2, we get 50.0 grams divided by 28 point, is it 02? I never remember. 28.02. So what is our moles of nitrogen? 1.78 moles. So can I decide comparing these two numbers? Nope. I need to figure out how many I need for the sandwich, 3 and 1. So I need to divide this by 3 and divide that by 1. And so what do we get? 0.416 compared to 1.78. So what is in excess? Nitrogen is in excess. This is the limiting reagent, and we're going to stoich over to solve for grams. So let's start. You can start with the 50 grams if you want, but we did a little legwork already. What did we calculate here? Moles. So I'm just going to start with those moles. Why do the same work twice? So I've got that many moles of calcium. What's my mole ratio to the product? 3 to 1. For every 3 moles of calcium on the bottom, I have 1 mole of calcium nitride. And then how do I find grams? Molar mass, right? For every 1 mole of calcium nitride, I have 148.234 grams. All right, so to 3 sig figs. $61. Can I get a second on that? Since it's a video, I want to make sure our final answers match. Okay, so I'm going to ask you a question, and I want someone to help me try to explain. What if I ask the question, how much nitrogen was in excess? Any ideas what we'd do? Sai.
You take however many moles, like the moles of calcium, compared to how many moles of nitrogen you use.
So you're saying you stoich to here?
Yeah.
Correct.
How much leftover we have by subtracting like that number of moles from 1.78.
Okay, we probably want to do grams, though. Molar mass. That's exactly right. So what you're basically doing is doing stoichiometry from calcium to nitride, or nitrogen, and that's going to tell you how much reacted. Once you know how many grams reacted, all you do is subtract it from 50, and that's what's in excess. Okay, so if they ever ask you how much is in excess, do stoichiometry from one reactant back to the other reactant. Okay? All right, good job. Let's do another one. Now we're going to talk about, in addition, we're layering now. Now we're going to talk about percent yield. So we use stoichiometry to find amount of product produced, and then we use percent yield to see how well the scientist did in his or her reactions. Does anybody remember what percent yield its formula was? That's percent error. You're close. It's actual over theoretical times 100. Actual is what you got in the lab, what you actually did. Does anybody remember theoretical, what that is? Yep. Theoretical is, when you do the math, what you should theoretically get. The way I used to remember this, I remember as a student, because, you know, I was there one day. I was in your chairs. not literally these chairs, but I was in your shoes, not literally your shoes either, at some point in my life. And I remember thinking, okay, if you're finding your grade, your actual grade over the theoretical, what's your theoretical grade, your perfect theoretical grade? In a perfect world, you get 100. So it's the perfect on the bottom, what you really are shooting for, with the actual on the top. Okay? So we need to look at this problem and probably write a reaction. It says methanol, also called methyl alcohol, is the simplest alcohol. It's used as a fuel in race cars and is potentially a replacement for gasoline. Methanol can be manufactured by combining gaseous carbon monoxide and hydrogen. So we're going to combine gaseous carbon monoxide and hydrogen to make the methanol. Anytime we write an equation, what should I do with that equation? Balance it. So it looks to me like I'm only short on H's on this side. So I'm going to put a 2 there. So then it goes on to say, suppose that 68.5 kilograms, bless you, is reacted with 8.60 kilograms of hydrogen. Calculate the theoretical yield of methanol. So what we're looking for is grams or kilograms, depending upon what we decide to convert to. We're looking for the mass yield. Theoretical yield is what we should get perfectly if everything goes perfectly well. But then they say, well, if 3.5 times 10 to the 4th, 3.57 times 10 to the 4th grams was actually produced, what yield is this? This is the actual yield. So I'm already ready there. All I need to do is figure out my theoretical, plug it in there, and then I can figure out my percent yield. So let's do our steps now to figure out our wonderful theoretical yield. What am I going to stoich from? Do we know? No. What do we have to find? The limiting reagent. So I'm just going to make life simpler and immediately convert this to grams because I don't speak kilograms because of the molar mass that we use. The molar masses are in grams per mole. We have to start with grams. Kilograms will not work. All right, so what's the first thing we do with these grams? Divide by the molar mass. So carbon monoxide is 12.01 plus 16. 28.01 grams per mole. And then this H2 is 2.02, right? So tell me the moles of CO. Okay, 2,400. So let's just do 2,450. 3 sig figs, is that right? All right, this is moles. And then what is my moles of H2? That? All right, so there are my 2 moles. So before I can actually decide which one's limiting, I need to see, based on the mole ratio, what's going to run out first. So this one is a 1 to 2 relationship. What is 4260 divided by 2? 2130. So who's going to run out first? Hydrogen's going to run out first. This is my limiting reagent. This guy is in excess, right? So now I can start. I'm going to go ahead and start with my moles here. I don't really want to redo that work. So my hydrogen is 4, 2. That's a lot of moles. Moles of H2. What's my goal again? I feel like we've done so much work and we still haven't really made much headway. What's the goal of this problem? To get what? Yeah, we need that theoretical yield of methanol. So for every 2 moles of hydrogen, I'm going to stoich on over, mole bridge, I have 1 mole of CH3OH. That was my stoichiometry. Okay, what's the molar mass of methanol? Thank you. Sai is on it today. 3 sig figs, please. 68,300 grams. Okay, So that's 6.83 times 10 to the what? Is it to the 4?
Yeah.
So I just like it in the same format. So that is my theoretical yield. This is if it were perfect, based on the math, what I should get. Well, we can see, looking at this percent yield calculation, not so great. What is our percent yield of our experiment? 52.3?
Yeah, 32.3.
Okay. Do y'all have questions? How y'all feeling about that? All right, let's keep going. We have this problem and one more. We're almost done. Okay, so this is yet another problem that we're ultimately, if you look through, first we find the limiting reactant, then we find the theoretical yield, and then with this given actual yield, we want to find percent yield. So, first thing we need to do is find the limiting reagent. I have 3 reactants this time, and so I need to find moles of every single one of those. To save us some time, I'm going to have the first 2 rows, you guys find moles of AS2O3. You 2 rows do the moles of I2, and you guys on your own with water. Go ahead and get me the moles. I'll start writing out the moles in words here. All right. AS2O3. Great. 0.0126. All right. I2.
0.0177.
Second on that? I only heard one voice out of 10 people. Yeah? Okay. And then moles of water? 0.222? Okay, so those are our moles. So before we can decide limiting, let's go ahead and divide by the coefficient in those balanced equations to get a better idea of how much we need. It's a 1 to 2 to 2 ratio. So this comes out to be 0.0126. This one comes out to be, that's small. And this one, 0.111, right? So it looks to me like that's our limiting. Okay, so that's all the question was asking for, which was the limiting reagent for this part. So the limiting reagent is I2. And just so you know, if you use that kind of thing on the AP, you kind of need to define it ahead of time. So somewhere on the page, write limiting reagent equals LR. And you're not going to do that unless it's something you're using a lot. Otherwise, just write the words limiting reagent or reactant. Either is fine. Okay, calculate the mass of AS2O5, which is theoretically possible. So we have moles here of our limiting reactant. So let's go ahead and stoich on over from our limiting, well, here's limiting. That's excess, that's excess. We're going to stoich on over to figure out the theoretical yield of AS2O5. So 0.0177 moles of I2. How do I stoich over? Correct. For every 2 moles of I2, I have 1 mole of AS2O5. And now I just need grams. So we got a 129.84, 229. Thank you for being quick on that. This is per mole. So my moles cancel, and that's how many grams per that mole. So to 3 sig figs, what's our theoretical yield? Is it? I think it's like, I thought it was 2 something. 2.03 grams, okay? So, actual over theoretical times 100. Our actual yield is only 1.80. Our theoretical yield is 2.03. What do we get? 88.7? Okay. Yay. That's better than 50% in the last problem. So this year we're actually going to get to run some experiments where you will test your percent yield. So, and I just heard a number, someone shouted out a number that was actually smaller than 1.8. Can you have a percent yield that's over 100? Any ideas? You actually can. Let's say I'm making a solid. What would lead to over 100%, do you think? If you have impurities, maybe you didn't rinse off enough of the reactants. Okay, so sometimes things will weigh more than they should. Maybe you weigh a precipitate and it's kind of wet and it weighs more than it should, or there's other impurities involved. So above 100% theoretical yield is possible, but it means you're dirty. Something about you is dirty, whether it's your precipitate, whether it's not dry, something like that. Lab skills need to be cleaned up. Okay, so now we get to the last problem. Big, sexy problem of the unit. Remember the cough? You will see this on the test, I promise. Not this exact problem, but anything that's combustion analysis. Now, do you remember when I said we were doing homework 1F, I'm like, don't freak out if you can't do it, try it. Remember that? That's because it was this kind of problem. So I'm expecting you at some point to go back and try that problem once I teach you how to do it. It's a pretty set procedure. Once you see it, you're going to be like, oh, that's not hard. It's just kind of knowing which way to go. So here this says we have a 0.003 gram sample of naphthalene, a compound containing only carbon and hydrogen. So we don't know the formula, and our job is to find the empirical and then the molecular formula of this thing. Only thing we know about this is we have 0.00300 grams of it, okay? And they give us an equation and say when it's burned in excess oxygen, that's combusting a hydrocarbon. You know the formula, the reaction, when you combust a hydrocarbon, what do you get? CO2 plus H2O. We can't balance it because we don't know how many C's and H's we have, but they did tell us something. They said, hey, you produced 0.0103 grams of carbon dioxide. Determine the empirical formula of naphthalene, and the formula weight is given to us at 128. And then they also want the molecular formula. Wow, they want a lot without a lot of information given to us, right? So let's think to what we have to do. We have to find an empirical formula. Any empirical formula problem that you've had, what did you know about the atoms? You're always given information about atoms before you have to find an empirical formula. What is that information? Percents. What did you do to those percents immediately? Turned it to grams and then convert to moles and then find the mole ratio, right? So we need grams. We need grams of this stuff. And that's what this is going to help us find. Okay, you know I keep talking about the conservation of mass and matter. Can we all agree that the carbon that's produced all comes from the naphthalene, right? So is it fair to say we have the same number of grams of carbon in the product and reactant? Yeah, we do. So what we're going to do is we're going to do a little dimensional analysis within, not stoichiometry, just within the CO2 to figure out how many grams of carbon are actually in this many grams of carbon dioxide. So I'm going to start with my given 0.0103 grams of CO2. And just like everything else, I want to convert to moles to get to a mole ratio. So for every 1 mole of CO2, I have, 44.01 grams of CO2. So how does that help me? How am I going to get to grams? Remember, my final thing here, I want grams of carbon. Cameron. Perfect. Remember that in every 1 mole of CO2, I have 1 mole of C, right? Remember that? That whole car thing, if I have a mole of cars, I've got a mole of steering wheels. If I have a mole of cars, I've got 4 moles of tires. So our atom ratio is the same as our mole ratio. So for every 1 mole of carbon, I have 12.01 grams. So that gives me grams of carbon. That's fantastic news because I need grams of carbon to find my empirical formula. So to 3 sig figs, how many grams of carbon did you get? I'm checking numbers because this is where our debacle was in second period, so I want to make sure our numbers are right. I trusted too many people in second period. It was bad. What did y'all get for grams of carbon? 281? Yay, that many grams of carbon. That's awesome. So now what I want to do, I want to know to 3 sig figs how many grams of hydrogen. Well, I don't know anything about hydrogen. Do y'all have any idea how I can figure out grams of hydrogen? Yeah, don't we know the full mass? Well, if it's only got carbon and hydrogen in it, if I subtract, isn't the rest hydrogen? Yes, it is. So when you subtract, you get 1.99 times 10 to the negative 4 grams. That's awesome. Now it's just a normal empirical formula problem. You're done with the hard stuff. So now, to go from what do I do next? Grams to an empirical formula to moles. So I'm going to divide this by 12.01 and this by 1.01. And when I do that, I get 2.34 times 10 to the negative 4th moles. Oh, pen, don't die. And then 1.87, oh, what am I doing? Yeah, 1.87 times 10 to the negative 4th moles of hydrogen. Now, I have moles. How do I continue to find the mole ratio? What do I do? Divide by the smallest moles. Okay, I want you to put this in your calculators. I know I did these calcs for you. These numbers are good. So 1 here. What do I get when I divide? 1.25. Interesting. Huh. Can I have a formula of C 1.25 to H? Multiply it by 4. And what do we get when we do that, Aniston? What do we get? It's okay. You've got 4 plus 4 quarters. C5H4. Okay, so can we make sure this is our empirical formula? What would be a way to check that we're right? Look at we know the molar mass of the molecular formula is what? 128? Yeah? So what was the molar mass of this empirical formula? 64. Huh. What's the relationship there? Times 2. So what is our actual molecular formula? H8. And that is naphthalene. So I'm going to draw naphthalene for you and show you what it looks like to show you that. But the reason I'm recording this period, because what happened last period, we had a bad rounding situation here, which led to this number being 1.17 or something. Don't write that down. But when you did that, they rounded this to 1.2, and I just let them go because I knew it was wrong. If you multiply 1.2, so let's pretend it's 1.2. 1.2 times, what would you have to multiply to get a whole number? 5. So our formula in second period ended up being C6H5, right? And I'm like, okay, well, figure out the empirical form, the molecular formula. And they realized this came out to be like 74 or something like that. 74 doesn't divide evenly into 128. And I wanted them to see that that's the wrong answer. So you will know the second you get that empirical formula mass whether or not your answer is right or wrong. So there's never a reason to miss it, because you will always be able to check your work that way. So the way naphthalene looks, that's C10H8. And I remember this specifically because I don't know why my high school teacher had this. She had a poster that it was hand-drawn. So these are two benzene rings, and you take organic, you'll learn about alternating double bonds. In pre-AP, you did benzene a little bit, right? But she ended up having this little dude, and it's drawn on the side, but I'm drawing it for the video. He's all hairy and whatever, little mouth, and he's like mad. So he had a little bubble up here that said, thought bubble, I hate moths. Does anyone know what naphthalene is? Mothballs. Have y'all ever smelled mothballs? They're really gross, but I know that my mom used to keep a Hope chest from her mom or something, and there were these mothballs in them. Whew. So anyway, they keep away moths. So naphthalene is two benzene rings attached, and each carbon, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons, and then there's 4 hydrogens on each ring. That's just a little beyond what you need to know. So your homework tonight is, of course, required, but if you turn the pages in your packet, and if you don't do the packet online, there's an additional page called Combustion Analysis Practice. I'm not requiring that, but if you want to, I do need to tell you one other thing. If you want to practice, I want you to do some on that sheet, and the answers to that are also posted where the homework answers are in. Now, let me just talk about another version of this problem with if we have an additional element like oxygen. Want to make sure you know how to handle this. So, don't write this down, just watch. Let's do a different color. Let's do a very different color. Let's pretend your element that you didn't know anything about had an oxygen in it. Okay? The difference in the problem would be, in addition to giving you the grams of CO2, they would give you, I don't know, I'm making things up, they would give you grams of water as well. So what you would do is you would do dimensional analysis, just like here, to get your grams of carbon. Then we do dimensional analysis here to find the grams of what? Oxygen? Why not oxygen? Because look, you got oxygen here too, right? So if you can do oxygen, but you'd have to do dimensional analysis here and add them up. We want to do hydrogen because this is the only place hydrogen is outside of that compound. So you would do dimensional analysis again here. And then in your total grams, you subtract off your carbon grams, you subtract off your hydrogen grams, and that would give you your oxygen grams. Okay? So it's the exact same problem. You just have one extra step, one extra dimensional analysis to do to get grams of hydrogen, okay? All right, now I'm done.